So we want to continue with this idea of series resonance in order to define some key parameters that we can use to characterize the quality of the resonance. So I have here our plot for our current magnitude from the previous video. And so note we said our current magnitude is going to be a maximum value of Vm over R at our resonant frequency. And then we somewhat arbitrarily said, let's also designate two frequencies, omega 1 and omega 2, which occur when we have half of the maximum power being dissipated in the system. That half power corresponds to a current magnitude that we see here. So I've got that down below as well. So our half power occurs when our current magnitude is equal to Vm divided by root 2R. And so we can note in general that our current magnitude is Vm times the magnitude of our impedance, our equivalent impedance. So essentially what we can do is we can equate our equivalent impedance to this root 2R in order to solve for values of these two frequencies, omega 1 and omega 2. So let's do that. So previously we had said that our equivalent impedance can be written as square root of R squared plus the quantity of omega L minus 1 over omega C squared. And we're saying that is equal to square root of 2 times R for this half power case. So what we can do is we can start by squaring both sides. So we're going to have R squared plus the quantity of omega L minus 1 over omega C squared is equal to 2 times R squared. Well, now we can move this R squared, subtract that from the right side, we get a 1R squared, take the square root, and what we're going to have is the quantity omega L minus 1 over omega C is equal to square root of R squared, which is equal to plus or minus R. Okay, so what we can do now is we can move this R over to the other side, so we have everything on the same side, and multiply through by omega. And what that's going to give us is omega squared times L minus plus omega times R minus 1 over C equals to 0. And so what we see here is that this is a quadratic equation. So we have our A, our B, and our C values. And so this is going to give us 4 possible solutions, but only 2 of them physically make sense. So 4 possible solutions, but only 2 physically make sense. And so that's due to that resistance value. We want that value to be positive in order to make physical sense. So if we calculate that, we're going to get values for our omega 1 and our omega 2. So we're going to have for omega 1, it's equal to negative R divided by 2L plus the square root of the quantity R divided by 2L squared plus 1 divided by LC. And our omega 2 is going to be the same thing, but we're going to have a positive R over 2L. So plus square root of R over 2L squared plus 1 over LC. And so again, to be consistent with the notes, I'm going to label these as equation 2 and equation 3. And what these are called our half power frequencies. So our half power frequencies. And so again, if we come up here to our plot, we can see that those are the frequencies at which our power has dropped by half, or our current magnitude has dropped to about 0.707 of its maximum value. One other thing to note in terms of a relationship between our resonant frequency and these two half power frequencies is that the resonant frequency is the geometric mean of omega 1 and omega 2. That is, it is equal to the square root of omega 1 times omega 2. So geometric mean. So the next thing we want to focus on is another parameter we can use is the difference between these two frequencies. And so a term that you might have heard before is something called bandwidth. So we can define a bandwidth B, which is the difference between omega 2 and omega 1. And so this is going to make it easier, again, as we get into our filters. We can talk about frequencies falling within the bandwidth or outside of the bandwidth. And in this particular case, because omega 1 and omega 2 correspond to our half power points, this is going to be a half power bandwidth. So we can define B as being omega 2 minus omega 1. And we say this is our half power bandwidth. And to be consistent with the notes, I'm going to label this as equation 4. And so as I've mentioned a couple times in previous videos, it's somewhat arbitrary to have chosen half power. However, half power is commonly used. For instance, if we wanted to, we could have also defined a quarter power bandwidth. A quarter power bandwidth. We could have also done it based on voltage magnitude. Maybe we wanted to do a half peak voltage magnitude bandwidth. So we could really do sort of anything we want, but again, this half power bandwidth is pretty common. So one other sort of key parameter that we want to define is going to quantify sort of the sharpness of our resonance. So we can quantify our sharpness of resonance with something called the quality factor. So our quality factor, we're going to denote it with the letter Q. So one thing to note, this Q, of course, if you're talking about power, has a different meaning. So this does not mean reactive power. So make sure you don't get that mixed up as you're looking through here. And so we can define our quality factor in one of several ways. We can define this as omega naught L divided by R. We can define it as 1 divided by omega naught C times R. Or we can define it as the square root of L divided by C R squared. And so again, to be consistent with the notes on Canvas, I'm going to label this as equation 5. And so what you can notice now is we have 5 of these equations, 4 in this video and then 1 in a previous video where I've labeled with these blue numbers. And so we can characterize our resonant circuit with these 5 variables. So our resonant circuit is characterized by 5 related parameters. And so again, we talked about 4 of them here. We have our half power frequencies, omega 1 and omega 2. We have our bandwidth, we have our quality factor, and then the only one that we had presented in a previous video that wasn't here explicitly was our equation for our resonant frequency, omega naught. So we have these 5 different related parameters to specify our resonance, but they're not completely independent. So let's put but. Only 2 of these can be specified independently. Okay, and so I'll come back to what that means here in a second. So only 2 can be specified independently. And so basically what that means is once you know 2 of those parameters, the other 3 are set. So for instance, let's say we know what our omega 1 and omega 2 are, or maybe we design for a certain omega 1 and omega 2, then that automatically sets our other 3 parameters. So all of them are not independent, they do have some dependence on one another. One thing that I forgot to mention related to our quality factor here is typically we would call this a high Q or a high quality factor circuit if we have Q greater than or equal to 10. And so this sharpness or resonance, again, it'll make more sense once we get to filters, but basically the higher Q, the more selective a filter is going to be. So now we have sort of a basic idea of this resonance circuit. In the next video, we're going to look at some alternate forms for these 5 key equations. Then we're going to look at an example. And then finally, we're going to look at using a slightly different RLC circuit, a parallel RLC circuit, and see how the resonance equations differ.